Good evening to all. In the last class we have started the discussion on this structural dynamics, and I have started to give you an introduction to what is structural dynamics, then the importance of structural dynamics in civil engineering. That is, it is dealing with many type of dynamic loads that will result in the dynamic conditions. That is, the load will be varying with respect to time. Since the load is varying with respect to time, each of the parameters associated with that load, that is the bending moment, the shear force, the stresses, the deflection, the velocity, the acceleration, everything will be having a variation. So that is the complexity of this type of analysis, that is dynamic analysis. Then in the dynamic analysis we have discussed what is started with the variation of static and dynamic analysis. I am not going too much on that, as we have discussed in the last class. Then regarding the modeling of a structure, this one also we have discussed. That is, if I have to model a structure like this, first of all I have to create a mathematical model, a mechanical model. From the mechanical model I need to solve this by using a model that is known as mathematical model. So this is the way in which we will be dealing with any type of structure, be it in a dynamic analysis or any type of structure. First of all we will be producing a mechanical model, then we will be using some equations, mathematical tools, to formulate the equations and find out the responses. Now we ended the last class discussion with the systems, elements of a dynamic system, or the parameters. So whenever I am going to analyze a dynamic system, I need three parameters are needed for defining the system. For example, here you can see, if I am defining this system, what are the parameters I used? I need a load. Okay, this load is there. This load is supported by a frame like this, that is forming the beam. That is another thing. Then there is a support. So these were the elements of this system. Now whenever I am going for a dynamic analysis, I have having three elements. One is mass, stiffness, and damping. Now let us look into each of these elements today. So first of all, how can I model the mass? So that is, I am having a system, that is, for example, I am having a water tank. Okay, let us choose a water tank. A water tank is there like this. It is overhead water tank. It is supported by columns. Okay, the overhead water tank is there. It is supported by columns. So if I am going to model the system, first of all, there is mass. The mass is due to the water and the concrete. So this mass, I can model the mass in two ways. One is distributed mass, another is lumped mass. So distributed mass means if you are having a beam like this, simply supported beam, then we are assuming that the mass is distributed throughout the length. That is a real condition. In reality, we can assume that the mass is distributed throughout the length. The next type of model is lumped mass. So our discussion will be mainly on lumped mass, because distributed mass, it is again very different, very difficult, because the mass itself will be varying with respect to displacement. So that with respect to the distance. So that is difficult to model. So so in most of the analysis, in dynamic analysis, we will be having the concept of lumped mass. So lumped mass is like that. Here you can see the beam. I am keeping a mass like this, M. A higher mass is kept. So I will be analyzing the structure in such a way that this is my simplified structure. That is, this total mass plus small m. Small m is the mass due to the beam, self weight of the beam. Capital M is the load. Sometimes the load due to a machine. A machine is kept there, or load due to some another cross beam is coming to that beam at the center. Then that is the mass. So so the modeling of the mass, there are two types. One is distributed mass and lumped mass. So distributed mass means the total mass of the structure, or the weight of the structure, is assumed to be distributed throughout the beam in a UDL. You know that what is UDL, that is uniformly distributed load. But in lumped mass system, we will be assuming that the mass is concentrated at a single center. So that is the two types of mass. So our discussion, our way will be mainly on this lumped mass. Okay, so here you can see, for example, if I am having a beam like this, a beam is the model, the mass will be modeled like this. Here you can see, if I am having a, for example, I am having a load like this, and M is there. So this, how can I model this? I will be assuming that here my mass will be concentrated. The total mass will be concentrated here. So that will be M plus small m. Small m will be what will be the, this if this beam is a cross section, let the cross section of the beam be, for example, it may be 30 centimeter by 30 centimeter. So that, so the small m will be, what will be small m? Small m is equal to density of concrete. Density is 24 kilonewton per meter square. So density into the length into the cross section, that is breadth into depth. So that will be by small m. That plus capital M. Capital M is the concentrated mass. It may be a person is standing there, or a some hoardings are there, like that. So that is the total mass. So I am modeling this in this way. Okay. Now here some spring-like current that we will discuss. So the first parameter of a dynamic system, first element of a dynamic is mass. The mass is of two types. It can be modeled in two methods: distributed mass and lumped mass. So our discussion will be mainly regarding lumped mass. Second is, the second parameter is modeling of stiffness. So the second element is stiffness. How can I model this stiffness? So before going into this stiffness, you need to understand a term known as degrees of freedom of a this dynamic system. What are the degrees of freedom? Okay, so for example, here you can see I am having a beam, a simply supported beam. I am taking this example. I am having a simply supported beam like this. So I think you have heard about this term kinematic indeterminacy, that you may have studied in your structural analysis, kinematic indeterminacy. So here kinematic indeterminacy means it is the degrees of freedom which are required to define a system. So let me give a just idea about what is this kinematic indeterminacy. It was a term you might have studied in your structural analysis. I hope you have studied. For example, if I am having a bay like this, I am having two columns supported by a beam. So here the kinematic indeterminacy of this structure is, here at this point there can be a rotation. At this point there can be a rotation. Here there can be also another rotation, and here there can be a movement. Then since these are fixed ends only, in the fixed ends there will not be any movement. So kinematic indeterminacy or degree of freedom means it is the way the movements that are permitted. So here in a system like this, there will be one movement here, one, that is rotation, two, another rotation, three, there is a movement. So here the total kinematic indeterminacy is 3. So this is the thing which you have studied in the normal static analysis. But when I am coming into dynamic analysis, here the degrees of freedom is a different term. Okay. So here, for example, if I am having a this one is a framed structure which is having one beam is there. Here you can see a beam is there. Then here you can see this is a beam, this is a column, two columns are there. So if I am modeling this structure in a dynamic way, it will be modeled like this. That is, here you can see, here the columns we will be modeling as a single element, and the top there you will be having the mass. So that is this is the mass. So here the degree of freedom, it will be only 1, because this degree of freedom means how this mass can move. This mass can move only in the horizontal axis. So the degree of freedom is 1. So in static analysis, the degrees of freedom of this system is 3. But when it is coming into dynamic analysis, it is only 1. Okay. Now here I am taking another example. This is a 2-story building. This is the first story. This is the second story. First story and second story is there. And this is a 1 and 2. You can see here 1 and 2. So here, how I will be modeling is that this will be modeled like this, because in a dynamic analysis, let me take dynamic analysis, I will be modeling it like this. There I am having one column. One mass is located here at this point. Another mass is located here. So this one will be M1 and this one will be M2. So here the degrees of freedom will be here at this level, at M1 level, it can move in horizontal direction. So 1 degree of freedom will be here, and in the M2 level there will be another degree of freedom. So what will be the total degree of freedom of this system? It will be 2. It will be 2. So this is the idea. So so the degree of freedom in a dynamic analysis, it can be defined like this. That is, it is a number of independent displacements required to define the position of all the masses relative to their original position. It is the number of independent displacements that is required to define the position of all the masses relative to the original position. That is, for example, in this case there is only one story is there. So here, if I have to define this, only one mass is there. It will be having only one movement in one direction. So here the degree of freedom is 1. But when it is coming into this structure, there are two masses. Here one mass is there, here another mass is there. So here I need 2 degrees of freedoms are needed for defining the system. So here this is 2 degree of freedom system. So there are, so one is 1 degree freedom system, 1 degree freedom system. Second is 2 degree freedom system. Like that, there will be different number of freedom systems. So this 1 degree freedom system, it is known as single degree of freedom, SDOF. This is an important term, SDOF. And 2 or more, it is known as multiple degree freedom system, or MDOF. So SDOF, it is single, SDOF stands for single degree of freedom, and MDOF stands for multi degree of freedom. Okay, single degree freedom and SDOF and MDOF. So I am just taking the syllabus once again. Here you can see this is our syllabus. So in our syllabus you can see here the first module, you can see SDOF, second module. So the first 2 modules we will be dealing with SDOF systems. Okay, that is single degree, there will be only one mass. Then in the next 2 modules we will be dealing with multi degree freedom systems, MDOF. Here you can see MDOF. Okay, and in the last module also we will be having MDOF. So this is the structure of our syllabus. So in the first class I have told that I will not be able to give a complete idea about what we are going to study, but now as at 1 or 2 classes I have been finished, you will be getting the idea on what I am going to say. So first module, 2 modules we will be dealing with SDOF system, and second, the other 3 modules we will be dealing with MDOF. So simply it means in the first 2 modules we will be dealing only with one mass. There will be only one mass. In the second case there will be more than 2 or more number of masses will be there. So it is known as MDOF system. So SDOF and MDOF system. Okay, let us go back to our discussion. So that is the things you need to understand in this degrees of freedom. So I have said this degrees of freedom in detail because this degree of freedom in static analysis is completely different when I am going in a dynamic analysis. So in a static analysis, this degree of freedom is found out as kinematic indeterminacy. have anybody heard about this term? Do you remember this term, static indeterminacy and kinematic indeterminacy? Static and kinematic indeterminacy. So somebody, someone please, you just be interactive also, otherwise it will not be very easy. So please type, if you are knowing that, you can type yes or no like that, or some responses will be good. Have you heard about this term, static and kinematic indeterminacy, in the structural analysis? Structural analysis is in, oh, you are studying structural analysis only in this sem, right? So up to what level you have studied in structural analysis? I mean, have you studied about this, how to find out the what we call the deflection and all? Have you studied Macaulay's theorem, then double integration method and all? That is d square y by dx square is equal to that things and all. In your fourth semester and all, have you studied about that, those terms? Okay. So I need to get an idea, that's why I asked. Okay. Anyway, so I think you will be studying these two terms. Okay. Basically, this our structural analysis. We are studying static analysis, dynamic analysis. So let me give you just an idea about. I'm not going too much on that, but anyway. If I am talking about static analysis, there are two type of analysis are there. One is force analysis and displacement analysis. Okay, so this force analysis, it is having different methods are there that you will be studying in your I think maybe in your syllabus and all. Then in your displacement analysis, there are different methods. So you will be studying about solving the structures in two type of analysis, force and displacement. So this force analysis, there we are using static indeterminacy, and in displacement analysis you are using kinematic indeterminacy. As of now, just have that idea only. Later on, when you are studying this dynamic the structural analysis, you will be getting more idea on that. Anyway, you just have an idea. So now only focus on what I am said on degrees of freedom. Okay, so degrees of freedom in our dynamic analysis. Then let me go to dynamic analysis. So here, so just understand this one. So I think it will be better. You will not be getting any confusion, as you don't know what is kinematic indeterminacy and all. So anyway, let me focus on only on this degrees of freedom in our dynamic analysis. So in a system like this, the degree of freedom will be only 1. So in this system, the degree of freedom will be 2. Now if I am having a string like this, okay, a string, I am holding a mass like this. So here, for this mass, what will be the degrees of freedom? Degrees of freedom means it is the possible movement in that mass. Okay, that is meant by degrees of freedom. So for this mass, for this spring which I have shown here, which I will mark this in red. So for this system, what will be the degree of freedom? Degree of freedom means it is the possible movements. So what will be the movement if I am holding a mass in a spring, in a row, in a string? Maybe it may be a steel or a thread like that. So what will be the movement? What is a possible movement in that mass for that m? So you just imagine I am holding a weight. A weight is there. The weight is been tied to a thread. Then I am just holding the thread at one point. Then I am just moving the mass. So what will be the degree of freedom of that system? How many degrees it can, in what all ways it can move? Will it be 1? Will it be 2? Like that? So please type your answers in your chat, or just you can unmute and say, or Then only I will be getting an idea about are you getting this topic or not. So I have said that this is the figure you need to focus on. So here I am having a support. I am just dropping a weight mass m using a thread. Okay, just let it be a thread. THRED, thread. So here what is the possible movement of this mass if the in this string, whether it can move only in a horizontal direction or whether it can move only in a vertical direction or like that. So what will be the number of degree of freedom of this system? So anyone please reply. Degree of freedom will be 2. So what will be the movement? What is the two movements it can have? One is horizontal, okay. Then another can be what will be the thing here? Degree of freedom means, just imagine that degrees of freedom just means that for example, if I am considering a point in a space, okay, I am considering a small point in a space. The point can move in vertical direction. There in a space there are three axes are there: x-axis, y-axis, z-axis. So the possible movements of a point, for example, I am taking a very small point like this. A point is there, okay, I am considering a small point. Here the possible movements are, it can move in vertical direction, it can move in horizontal direction. Let it be a 2D space, okay. I am considering only 2D, I am not going for 3D. Now next thing, this is the two possible ways. Then another possible way is it can rotate. So for a point in 2D, it can have 3 degrees of freedom. Degree of freedom means just the word itself, the freedom, the way, the possible movements we are permitting. Okay, so here the degrees of freedom is 3. If I am taking another example, I am having a fixed support. A fixed support is there. Okay, I am considering this point. So what will be the degree of freedom of this point? Fixed support means it cannot move. Can it move in vertical horizontal direction? No. Can it move in vertical direction? It cannot move. Can it rotate? It cannot move. So here the degree of freedom will be of this point in a fixed, it will be only, it will be 0 because there is no movement. Now when I am taking, instead of that, I am taking a hinge support. In a hinge support, can it move in horizontal direction or can it move in vertical direction, and it can move in, it can rotate. So what are the possible ways it can move? In a hinge support, because it is fixed, in a hinge support it cannot move in horizontal direction, it cannot move in vertical direction. The only possible way is it can rotate. So here the degree of freedom will be, for this point the degree of freedom will be 1. Okay, then when I am taking a roller support, I think you know what is the supports and all. In a roller support, here the possible, first of all you think about what are the possible ways. The possible ways are vertical, horizontal and rotation. So here in a roller support, here since the roller is like this, it can move in horizontal direction. So one movement is okay, but vertical movement, is it okay? No, vertical movement is not permitted, but the rotation is permitted. So here the degree of freedom will be, the DOF will be, degrees of freedom will be, it will be 2. So this is the way in which you have to think. So for this mass, this is the thing which we are discussing. This mass, it can move only in this direction. That is, if the string is, it's a not extensible spring, it can move only. So the degree of freedom of this system will be only 1. Because I am only giving a, at one time it can give only in, that is the degree of freedom will be 1. Now for another cases, if this string is extensible, if I am using, instead of a thread, if I am using a rubber band, so what will happen to the rubber band? It is having elasticity. So what will happen? It can move in this direction as well as it can move in this direction also. So the degree of freedom will be 2. So the degree of freedom depends upon not only on the mass, number of masses, but it also depends upon the property of these elements or the columns or the threads which are holding these masses. So that is the way in which you need to understand this topic. Okay. Now here you can see this is a very simple system. Here the degree of freedom will be only 1. Now here you can see another system. Here this is a simple, this system only, this one it is drawn like this. 2 masses are there. So here the degree of freedom is 2. Now again another system you can see here. Here a mass is held out horizontally and vertically. So here it can move in 2. So here it will be 2. So here you understand that only one mass is there, but it can move in 2 directions. So the degree of freedom is 2. So in the first 2 modules, our discussion will be mainly on a system which is having only 1 degree of freedom. Okay. So now so that is the degree of freedom. Now let us look into the next case. So first model we started is modeling of mass. Then I go on to degrees of freedom. Now I am going to discuss about the mass we have discussed. Now it is stiffness. So the stiffness, I think you all know what is Hooke's law. Hooke's law is the stress is directly proportional to strain, or stress is equal to a constant into strain within elastic limit, and that constant is known as Young's modulus. That is another Hooke's law. So according to Hooke's law, I can represent, if F is the force and K x is the displacement, then F is equal to K into x, where K is the stiffness coefficient. So the stiffness is modeled like this. Stiffness can be modeled. So the force due to stiffness is K into x. Okay. Now if the Hooke's law is not valid for Hooke's law is valid only for linear conditions. Then for non-linear conditions, this we cannot take this into criteria. But our main discussion will be only on linear cases. Okay. So that is the stiffness. So stiffness can be modeled like this. Stiffness is equal to a stiffness coefficient into, let the stiffness coefficient be K, and if the displacement is x, then that is equal to K into x. So that will give us the force due to stiffness. Okay. Next, third component is damping. So here you can see damping. So let us look into, here you can see a vertical rod. The vertical rod is fixed at a point. So what will happen to this rod? If I am pulling this rod to one end, what will happen? It will vibrate. The first vibration will be like this. Then after vibration, will it come into the original position? No, it will be vibrating to the other side. So like that, it will be continuing the vibration. But this will be the first movement. This will be the first movement. Let that distance be x. Let it be x. Will the second movement will be also x? No, it will be reducing. So due to what things, there will be some, these are the conditions in which the reduction in the amplitude will take place. That is, one is due to the friction at the joints. Here there will be friction. Then another is due to the temperature. Then due to sound energy. Then it is due to damping devices. Then some damping devices may be there. So for example, if I am constructing a large building, maybe for example if I am taking into example a building like a 100-story building or a 30-story building, during the earthquake, what will happen is that the building will be vibrating. So we will be constructing some damping mechanisms to reduce that vibration. Okay. So the relevance of this damping comes there. So the subject we are dealing with is mainly considering, when I am planning a building like that, I need to plan this damping, how to reduce the damping, how to increase the damping. I will be giving artificial damping mechanisms. There are different mechanisms are there. Those things we will be studying in the 5th module. A small introduction will be given in the 5th module and all. So that will be the application level of this damping. Okay, let us. So here, the damping, it is mainly represented in this way. That is, it is known as a dashpot model. So it will be like this, and the damping is represented as C. C represent damping coefficient. Then the force due to damping, force, this is a force. Force due to damping is C into x dot. X dot means it is, so we are having x, then we are having x dot and x double dot. Okay, x dot means we will be representing a dot like this. X double dot means two dots we will be keeping. X dot, it is x, it stands for displacement. X dot stands for velocity, and x double dot, it stands for acceleration. Okay, so x dot, x dot and x double dot. Okay, so this is the three things that when I am explaining the next slide, you will be getting an idea on that. So the elements, there are three type of elements are there: mass, stiffness and damping. So the mass, so what we are going to find is that I need to find out the forces. That is the thing. So due to the mass, the force is given as, so here you can see the force will be given as F. That force is equal to m into a, mass into acceleration. So m, that is the acceleration will be denoting as m into x double dot. So x double dot we are writing like this. In the top we will be having two dots, that is x double dot. Then due to stiffness, it is Fk, I am just denoting as Fk, that is equal to k into x, that is displacement. Then in the damping, it is Fc, that is equal to c into x dot. So these are the three forces that will be coming in a system. Okay, so then how the forces, and so a single degree, now our discussion will be mainly on single degree of freedom system. So a single degree of freedom system is represented like this. So first of all, what are the elements? Three elements are there. One is mass, second is stiffness, third is damping. Fourth one, it is the external force. That is the external force. Sometimes the external force can be zero. Sometimes the external force can be different. Okay, let it be like that. So the three elements of a single degree of freedom system are mass, stiffness and C. So I am just drawing once again. So if I am having a support will be there, let this be the mass, this will be the my first element. Now the stiffness, it is represented as like this, a spring. Okay, and the damping, it is represented like this. These are the symbols that we use. So here the stiffness, it is the coefficient is K and the damping coefficient is C, and this is known as a mass less spring, and this C, this is dashpot model. Okay, to just say how we most of the textbooks it is been written like that. Okay, mass and stiffness. So this is the diagram which represents how we are modeling a single degree of freedom. Now after modeling, so this is our mathematical model. Now after modeling this, I need to develop an equation. Okay, now how can I develop the equation? So that equation for this system can be developed by two methods. One is by using Newton's second law, second is by using D'Alembert's principle. So I am just showing the final equation. This is our equation. Okay, this is our equation. Mx double dot plus Cx dot plus Kx is equal to F of t. F of t is the force. Why we are F of t? Because it is dynamic load. So this equation can be generated by two methods. One is by Newton's second law, and first of all let us look into Newton's second law. So Newton's second law, first of all we will be drawing the free body diagram. So here you can see I am drawing the mass. So this is regarding the Newton's second law. So here F of t, it is the external force. Now due to the stiffness, I will be having K into x. Due to this damping, I will having C into x dot. So now you can see here the total forces. The total force will be F of t, it is to the right, other to the left, it will be the opposite direction. So f of t minus cx dot minus kx, that will be equal to a unbalanced force. Now what is Newton's second law? The Newton's second law we have discussed in the last class. That is, according to Newton's second law, here you can see the unbalanced force is equal to mass into acceleration. So here I have got the unbalanced force. So f of t this unbalanced force is equal to m into x double dot. So if I am just rearranging, I am taking these two terms to this side. So what will happen? Mx double dot plus cx dot plus kx is equal to f of t. So this is the equation of a single degree of freedom system, which we have obtained from Newton's second law. Now let us look into how we are taking it in a D'Alembert's principle. So in D'Alembert's principle, first of all I am drawing this similar to this figure. I am drawing the free body diagram. Now according to the D'Alembert's principle, here this body is tending to move in towards the right direction, okay? But according to this principle, when a force is trying to move in the opposite direction, in one direction, another force will be acting in the opposite direction. That is known as inertia force. That inertia force is equal to mass into acceleration. Okay, mass into acceleration. So this red thing which I have written here, that represents the inertia force by the D'Alembert's principle. So both the ways you will be getting the same equation, but what is the difference? The difference is, here we are using the Newton's second law. By using the Newton's second law, I will be finding out the unbalanced force, and I will be equating for that unbalanced force. That unbalanced force will be equal to mass into acceleration. And here I am drawing the free body diagram. Then in the free body diagram, using the D'Alembert's principle, according to the principle states that if a body is moving in one direction, it will be opposed by another force in the opposite direction. That force is equal to inertia force. Inertia is equal to mass into acceleration. So what is acceleration? Acceleration we are representing it as m into x double dot. X double dot. So I am just writing. So as per the equilibrium, I can now consider the equilibrium. I am taking equilibrium condition. The net force should be 0. Therefore I am writing equation of motion will be mx double dot plus cx dot plus kx is equal to f of t. So in both the ways you can find out the equation. Both will be the same. So just to have an idea about how to how to find out the equation of motion of a single degree of freedom system. So a single degree of freedom system, this is the mechanical model. Now by using both methods, by using Newton's second law and by using D'Alembert's principle, I have found out the equation of motion. Now I need to solve this. That is, this is a higher degree quadratic equation. That is, you know what is quadratic equation and all. Our normal equation is y is equal to mx. That is the first degree equation. Second degree equation is y is equal to that is y is equal to m into x plus c. That is our first equation. Second degree is equal to y is equal to a into x square plus b into x plus c. Similar equation only it is written here. M into x double dot is x square plus b into x plus c. Same only we have written here. Now we need to solve this. How we are solving a quadratic equation? I think you remember. If such an equation is there, we can write x is equal to minus b minus plus or minus b minus square root of b square minus 4ac divided by 2a. The thing, I think you just remember in the max and all you have studied. Similar way we will be solving this, but here we need to take sine theta, cos theta and all that we will be discussing in the next class and all. So this is the thing which I need to discuss on this class. So today I have discussed about, we have started from the last class, that is the elements of a degree of a dynamic system having 3 elements. how to formulate the model these elements I have discussed. Then we discuss about a small term known as degrees of freedom. Then in that we need to study about single degree of freedom and multi degree of freedom. So single degree of freedom is SDOF and multi degree of freedom is MDOF. Then now we are having, then I will wind up with one small just for 2 minutes I will wind up this one. So what things we are going to study is that I am having this equation, I am just using this equation. So this is our equation for just focus on this equation, mx double dot plus cx dot plus kx is equal to f of t. This is our equation. Now here sometimes this force, it may be 0. If this force is 0, then it is known as free vibration. Okay. Now if the force is there, it is known as if the force is there, it is known as forced vibration. Okay, free vibration and forced vibration. So in free vibration, this f of t is equal to 0, but in forced vibration the f of t is not equal to 0. So now again this is of this free vibration and forced vibration, this is of two types, 1a and 1b. I am just noting it, 1b. That is, sometimes this damping, it can be 0. That is one case. If the damping is 0, then it is known as damped free vibration. Okay, damped free vibration. Then sorry, this is damping is not there, it is known as undamped free vibration. Now next is this C is not 0, there is no there is damping is there, then it is damped free vibration. Okay. Now similar way, in the forced vibration also there will be undamped forced vibration, and it can be, another thing is, what will be the other thing, damped forced vibration. Okay. So these are the four conditions. One is the force can be 0, it is generally known as, when the force is it is known as free vibration and forced vibration. Again the free vibration is of two types. Sometimes the C is 0, it is known as undamped condition. In the undamped itself there are undamped free vibration and damped free vibration. Here undamped forced vibration and damped. So these four cases we will be studying throughout our this subject. So here you can see this is written, a free vibration, it can be undamped, here the force will be 0. Damped, here C will be not be 0, but force will be 0. In forced vibration, this force will not be 0, but in damped C will be 0 and undamped C will be 0, and damped means C will be there, damping will be there. So if I am taking the syllabus, you can now look at the syllabus. Here you can see the first thing we will be going to study is undamped free vibration. So what is the meaning? There the damping, the C factor, it is 0. Here you can see it is damped free vibration. Like that only we will be dealing with our subject. Okay. So as the is going on, you will be understanding each of these terms. So today I am ending this class with this one. SDOF system and MDOF system is there, and there we have just understood how to formulate the equation of motion. Okay. So that is here, you can see here the equation of motion of a SDOF system. Okay, the other things we will discuss in the next class.